but it was just a so I thought I had that thought later, like, oh, could have been the professor did this just to change the question so it's different from where they got it from. So yeah.
Okay, guys, let's get started. So we only have 3 questions for today, so it should be fairly quick. And like what is this? Okay. And like, how's your midterm? Good. Yeah. Like I think he posted the solution on the yeah. I didn't like actually did it myself, but I don't know if you feel good. Okay. Yeah. Okay. See. So like actually for today's peer section, like it's actually like you may notice like all those questions are from the suggested problem, and like for the last question for this one, the given answer is actually not correct. Like, yeah, like it's pretty weird. It's like in this question you can see like the coefficient for the spring is in inches. The distance is in feet, and the answer given is in meters. So it's like doesn't make sense at all. So like I did the last one like totally myself, and I think should be correct. I mean, like at least like all the process are correct. So anyway, let's start by the first one. So we have a 2 pounds brake, and this one is either like sometimes people call it pound mass, or like for me, I just recognize this one as the weight. So it's like actually a force unit, but not a mass unit. So this thing is sliding down at 5 feet per second. That is the velocity at the top. And we are going to determine the speed at this location, and also when it hit the ground, and also what's going to be the distance d. And like today we're going to use some new methods, and like that's actually my personal, like my favorite method to solve all those kind of questions. So I'm going to use the energy balance. So like I'm going to say the energy when the brake at the location A going to be equal to the energy at the location B. It's like the energy is conservative. It's like everything should be balanced. So that's like the principal equation I'm going to use. And then we're going to looking through like what's going to be the energy for the brake at the location A, and what's going to be the energy for the brake at the location B. So at the location A, we know that there's a kinetic energy at the location A plus the potential energy at the location A. And also the same thing at the location B is the kinetic energy at the location B plus the potential energy at the location B. And since the question told us the surface of this thing is smooth, it's a smooth roof, that means it's like we don't have any friction to kind of like waste the energy. So we can just keep doing that, plug in the equation. For the kinetic energy, what we have is half mva square plus the potential energy. So for the potential energy, for this question, I'm gonna say here is 0, or like the datum, like the ground is here. And at the location A, that is HA, and this one is HB. So the equation for the potential energy is the mass times the gravitational acceleration times the height. So those are the energy for the brake when it's at the location A. And everything gonna be equal to the energy at the location B. So the same thing, the velocity at the location B plus the potential energy at the location B. So here we have the equation, and then we just need to plug in the number to find the answer. So half, and the mass here is like, keep remember that what we have is kind of like weight units is a pound mass. So it need to be, oops, over 32.2. Like we are converting the mass to slug. N times the velocity, so that is 5 to the power of 2. And plus the same thing. Actually, for this one, it's going to be the weight itself. It's like we're over a 32.2 and then times a 32.2. And we times the height. So going to be 15 plus 30. And it's equal to half 2 over 32.2 times VB is something we're looking for, plus 2 over 32.2 times 32.2 times HB, that is 30 feet, 30. So like the rest of the thing is just the mass. So eventually we're gonna have things like 0.03105 V square. So that is 2 over 32. That is 1 over 32.2 VB square is equal to 30.78. So that we have VB square is equal to 991.3. Then VB is equal to, like mathematically, VB should have like two value. One is positive, another is negative. But like the negative velocity in this case just doesn't make sense. So we're just gonna keep the positive value. So we have 31.48 feet per second. So like see in this way, like if we are analyzing the energy, it's gonna be easier than before. It's like before we need to do like draw the free body diagram. We need to like see like what's gonna be acceleration in this direction, what's gonna be acceleration in another direction, like do all those like free body diagram analysis. It's gonna be like more complicated than this one. Like we're just simply thinking about the energy at the first state and the energy at the last state. So that is for the first part of the question, finding the velocity at location B. And then we're just gonna do the same thing to find the velocity at the ground. So I'll call it location C. This one. So the idea is gonna be the same. The energy at the point A gonna be equal to the energy at point C. Or you can also say the energy at location B is equal to the energy at location C. Doesn't really matter, but I'm gonna use the first one. So actually that is also a small trick when you're like doing exam. It's like if I'm saying like if here I'm using the energy at equation B, at location B equal to the energy at location C, and the energy at location B, I'm gonna definitely using the value I found over here. But like if you did it wrong at the first place and got the wrong value, the number you plug in here is also gonna be a wrong value. So like very small trick, just like keep what you have from the question. So like the equation is all gonna be the same. Kinetic energy at point A plus the potential energy at point A is equal to the kinetic energy at point C plus the kinetic energy or potential energy. potential energy at point C. So the kinetic energy at point A is the same, just the half mVA squared plus mgHA. The kinetic energy at point C is the value we're looking for, and the potential energy. So the potential energy, like since it's already hit the ground, the height is gonna be 0. So this one goes to 0. So we have a 0 here. The reason is since the height is 0. So we can just plug in the number, half times 2/32.2. VA is 10, remember? I don't know, it's 5. Times 5 to the power of 2 plus 2/32.2 times 32.2 times 30 plus 15 is equal to half 2/32.2 times the unknown. And then just do the math. You should have 90.78 is equal to 0.031056, the exact same number as before, VC squared. So VC is equal to 54.06 feet per second. So actually they're pretty similar, just like considering the energy at the first state and the energy at the last state to find out the number. I'm just double checking if I record a section. It's on the recording. Yeah. Okay, so the last thing we need to find is the distance D. So like to find the distance D, we cannot simply apply the energy rule, because like you see in the energy rule, we only have the velocity and the height. We don't have like a horizontal distance. So we have to go back to those like equation from before. So that's gonna be like draw a kind of like free body diagram, but actually it's not. It's just like we need to know the velocity at the location B and then like separate it into horizontal and the vertical component. And from the vertical component, we can find out like, whoops. In the vertical component, we can find out like how long does the brake gonna use to actually hit the ground, and use the time, we can find out what's gonna be the horizontal direction. So let's do that. At location B, we know that VB is equal to 31.48 feet per second. That's a new part. So that is the velocity here is VB. And like we need to find out what's the horizontal velocity and the vertical velocity. And it's actually given on here. So just a triangle with like the length of 3 sides. So from the geometry, we can know that in the vertical direction, Vy is equal to VB times 5/3. So that is 31.48 times 3/5. And the answer is 18.89 feet per second. And also Vx is VB times 2/5, 4/5. And that is 225.18 feet per second. And again, those information are from the geometry. So now we have the velocity in vertical and horizontal component. You can find out the time that the brake actually is flying, like it's dropping. So in y direction or in the vertical direction, we know the displacement usually is s, but I'm gonna use h here. It's equal to the initial velocity times time plus half gt squared. And this equation like is just this one, s equal to s naught plus t plus half at squared. And the h, we know that is hb, so it's 30 feet. 30 feet is equal to Vy is 18.89 times the time t plus half times 32.2 times t squared. And then we have a quadratic formula. So like you need to memorize the equation to solve the quadratic formula is negative b plus b squared minus 4ac over 2a. So that is the quadratic formula. And so if you, I'm gonna pause. And yeah, so we're gonna use this one to find out the value. And then for this one is t is equal to also like two values, one negative and one positive. But we're gonna use the positive value because like the time is not a negative value. So we have the time t is equal to 0.899 seconds. So that means like the brake gonna fly for this amount of time before you like actually hit the ground. And then the distance in the horizontal direction is just gonna be simple. It's gonna be equal to the velocity in the horizontal direction times the flying time t. And that is gonna be 25.18 times 0.899. And that is equal to 22.63 feet. Okay. So that is just the first question, like just a basic idea about how to apply the energy rule. So in the first equation, like everything's are smooth and there's no friction, so there are no like extra work from the friction. But in the last one, we're gonna consider friction. So we'll talk about that in the last one. And then we can go to the next one, the second one. So the given condition is the velocity or the speed of the box on the top is this one. So that is velocity VA. VA is this one. And we're going to determine the angle theta, like this angle, when the box is like flying out, it's leave the surface of the cylinder. So it's like when the box is actually flying out, there's only one force applied to this one, it's just the gravity. Like normally when this box is moving on the cylinder, there is a like supporting force from the cylinder, like N. But when the box is actually flying out, there's only a gravity because it's like flying, like there's no supporting force from the surface. And so we can also like first apply the energy rule. So this one is point A, and I'm gonna call this one point B. So the energy at A is equal to the energy at B. And since like everything is smooth, so we don't need to consider any energy consumption. And like it's gonna be the same thing, kinetic energy at A plus the potential energy at A is equal to the kinetic energy at B plus the potential energy at B. And for the kinetic and potential energy at point A, we have everything is given. So it's half mVA square plus mgHA. And I'm just gonna plug in the number. So half mVA square. So like the square root of GR/4 to the power of 0.5 is just GR/4. And the second one, mgHA. HA when the box is at location A is just R, like the radius. Then we need to consider the number at the unknown position B. And so like for the location at point B, or the potential energy at point B, it's gonna be the same, like HB and the HP. Actually, I'm gonna rewrite those things. Potential energy at B plus the kinetic energy at B. And the potential energy at B is the same as mgHB plus half mVB square. And the height at the point B is essentially this one. So like from the geometry, you can see this one is the radius R, and we're looking for this length, or you can project it to the front. We're looking for this one, and we know this is the angle theta. So now we have a triangle, and to find one side of the triangle, we just use cosine theta in this case. So it's gonna be HB is gonna be equal to this one's HB, R cosine theta. And then we're just gonna simply plug in this one into the equation. HB is equal to R cosine theta. So that is HB plus half mVB square. So now we are not sure like what's gonna be the velocity at this location. So we have like one unknown, and the other unknown is the theta, two unknown. So we need to find another equation or like some relationship to like fill into this equation to like find the VP. So now we can do the, we are going to do the free body diagram on this box. So that would be it. I'm gonna draw it here. When the box is just about to fly away at point B, the only force applied to it is just the gravity. And then we can project the gravity into also like two components. So the horizontal component, I mean the component that is normal to the center of the cylinder. And we have the theta angle over here and the other component. That is actually the speed is like flying out. So in the component that is like pointing inwards, pointing towards the center of the cylinder, is actually equal to the centripetal acceleration. So like in this force component is mg cosine theta, like that is the blue, I mean the purple component is equal to the centripetal acceleration. So that is mv squared over r, vp squared over r. The r is the small r in this case. So this is another like relationship we need to find. And then we are just going to simplify this equation and get vp. So isolating for vp, vp is equal to the mass is canceled out. It's gonna be rg cosine theta, square root of rg cosine theta. So we have vp here. And then we're just gonna plug in vp into our original equation to set up the whole like energy equation. So like, actually we know everything, so we just need to simplify the equation and then isolate for theta. So on the left-hand side, that is A1 over A mgr plus mgr. On the right-hand side is mgr cosine theta plus half mgr cosine theta. And then on the left-hand side is just 9 over 8 mgr is equal to 0 over 2 mgr cosine theta. Then you can see mgr gonna cancel out with mgr. So 9 over A is equal to 3 over 2 times cosine theta. So now we can solve for cosine theta. Cosine theta is equal to 3 over 4. And then theta can be found. And then theta will be equal to 41.4 degree. So that is for question 2. Like this one is for finding VB free body diagram for finding VB. So yeah, it's pretty straightforward. It's just another energy balance equation, and then yeah, just like fill in the equation. So the last one is a bit more complicated. So the question first is, the block is 25 pounds. This one is 25 pounds. And the initial velocity is 10 feet per second. 10 feet per second. So the block is gonna go to the right and then gonna hit a spring on here. When it hit the spring, it's actually like the kinetic energy gonna become the potential energy in the spring, and the spring gonna like spring it back. So like essentially it's just gonna go to the right and go to the left and then go to the right. So we know like the kinetic friction. So we have a friction. The coefficient for the friction is 0.4, and we're going to determine the total distance that the block can actually move. So before we do the question, we want all the units to be like conservative, like they should be the same. So like on here, like we notice like everything are actually in feet. So the speed is in feet, the distance is also in feet, but the given units for the coefficient of the spring is in inch. So first thing we want to convert this unit to pound feet. And 60 pounds per inch is equal to times 12 is equal to 720 pound feet. And we want to do the same thing for the left one, 120 pound feet. So for the unit conversion, you can use Google to do that. And another way is like, if you know like 1 inch, well, actually 12 inch is equal to 1 feet. So you know that the conversion is 12. So you just need to like, we are like pound over 1 inch. So essentially just times 12. If your receiving unit is pound inch, like if you want to convert pound inch to pound feet, you're going to over 12. Another thing, like when we're doing the energy calculation in empirical units, the unit is actually like a bit weird. So it's like in SI units, if I'm doing half mv square, like usually we're doing half the unit for mass is kilogram, and the unit for velocity is meter per second. And in this case, like the energy unit is in joules. But in like empirical units, we are using this one. So the mass, we want to use log. And the velocity, we want to use feet per second. And like the final amount of number, the unit is not joule, it's like some mystery empirical units. I'm not sure what that is. Like, I'm not sure it's BTU or it's pound force something, but like you just need to know it's not joules. Like this question actually confused me a lot yesterday. And like in second years, if you're doing mechanical aerospace, like when you're taking the fluids, you're gonna have a lot of like this kind of question. Like I have a friend, he's like in the second year fluids, and he's like every day he's dealing with those units. It's so like so tired about that. So like anyway, so like for this course, you just want to keep the units the same. Like if the question is asking for like pound feet or like feet or pounds, you just keep it like feet or pounds. And like in the exam, you just like don't write it out, like because we don't know what's the units over here. Okay, so let's go back to the question. So like the block gonna start moving to the right first. So it's gonna move to the right. So like we're going to solve this question like piece by piece. So it's like the first piece is from the original location to the far right location. And then we're gonna calculate how many like energy it's gonna consume. And then like when it's bring back, like how many energy it's gonna consume again to this one. And then like just doing like step by step. Oh yeah, so the first one, we wanna know what's the location at the original point. So the energy at the original point is just the kinetic energy, half mv square. And that is equal to half times 25 over 32.2 times the velocity is 10 to the power of 2. And that is equal to 38.82. Oh yeah, actually I wrote down the units over here. So like I Googled that yesterday, they said the unit is feet pound. So they said that is the unit for the kinetic energy in the imperial unit. Anyway, so like that is the total amount of energy we're going to consume. The initial energy, and then let's go to the second one. So this is E naught, the initial point. And then first we're gonna calculate when the block just hitting the spring, like just touching the screen, how many energy is left. So in this case, we can still like consider that as a energy balance. So the energy of the block at the initial point is going to be equal to the energy of the block at the final point plus the energy is like consumed by the friction. So this equation also means like the energy at the first moment going to be equal to the energy at the last moment. So E1 is half, well, actually we don't need to calculate what is E1. So just E1 plus the energy consumed by the friction is equal to F. So that is the friction times the distance that the block move, S1. So it's equal to E1 plus mu mg S1 equal to friction coefficient is 0.4. 0.4 times the weight of the block is 25 pounds. So 0.4 times 25 times the distance from E0 to E1 is 1 feet. On here, so times 1 plus 1 times 1. And they're equal to E0, which is 38.82 feet per feet pound. And like just solving this equation, we're gonna have E1 plus 10 is equal to E naught, or is equal to 38.82. So E1 is equal to 28.82 feet-pound. So that means when the block moved from the original location to the first location where it just touching the spring, around 10 feet-pound energy is lost, and there's only 28.82 energy left. And then the next step is the block gonna actually press the spring. So it's gonna move to another location, and we don't actually, like right now, we don't know what's gonna be the distance, like the compressing distance for the spring. E2. So next step, we need to find that. So the equation gonna be E1. The energy of the block at the location B is equal to the potential energy of the spring. So that is equal to half kx1 square. So this one is the potential energy of the spring plus the friction, like the work, like the energy lost by the friction. So that is Fx1. Energy. So this equation means all the energy at the location 1 gonna convert to the potential energy of the spring plus the energy wasted by the friction. So it's also a energy balance. And we don't have the kinetic energy in this case, is because like the block is actually stopped moving, so the velocity is 0. So this term gonna goes to 0. Things block stopped. So we can do that. The E1 is equal to 28.82, and that is equal to half of K. We found that K is equal to 720 x1 square plus Fx1. So again, it's another quadratic formula. Yeah, I need to plug in the F. F is equal to 0.4 times 25 times x1. So here's another quadratic formula. Just gonna use the equation to solve that again, and then we can solve for x1. So it's supposed to be equal to 0.269 feet. Let me check my calculation. 5. Yeah, that should be the value. So now, like we know, the block gonna move 0.27 feet to stop. So that is another like amount of distance the block gonna travel. So now we can calculate for E2. So what I mean by E2 is when the block, well, it shouldn't be here. So it's gonna be when the block like move from the E1 to here and then bring back to here. So that is E2. And the E2 is supposed to equal to the potential energy of the spring. K x1 squared plus the total energy like consumed by the friction. So 2 times 0.4 times x1. So this equation, the first one is the same thing, potential energy of the spring. And wait, 2 seconds. Fs, so 0.4 times 25 times x1. That is also the energy loss. Oh, actually, the potential energy of the spring is supposed to be on the other side. Square is equal to E2. That is because like the moment we're analyzing is like when the block is actually on here and the spring is fully compressed. When the spring is fully compressed, the energy in the system is all stored in the spring and there's no kinetic energy on the block. And then when you spring back to the same location at point B, like all the energy are actually from the spring, and also there's some small amount of energy consumed by the friction. So here is like the energy from the spring converted to the energy lost due to the friction plus the extra energy. That is the kinetic energy. So we're just gonna solve for this one. So E2 is actually equal to half K squared minus 0.4 times 25 times x1. 720 times 0.269 to the power of 2 minus 0.4 times 25 times 0.269 is equal to E2. So E2 is pound-feet. So the energy, like the energy you calculated is after the block hit the first spring, the spring B, the energy loss, the energy like remaining energy is 23.44 pound-feet. Okay, so now the block is actually going travel backwards, like it's traveling from B to A now, from B to A, going this way. So the next step we want to do is we want to find out what's going to be the energy left when the block is about to hit the spring A. So it's gonna be like how much energy is gonna consume when the block moving from point B to point A. So I'm gonna use E3 is equal to, so E3 is the energy at the spring A is equal to E2 plus the energy wasted by the friction. So F S2. And that is equal to 44 plus 0.0 mg S2 0.4 times 25 times 2 feet. Okay, so like this two, the location of these two, I put it on the wrong location again. So this one's supposed to be a E2 and E2 is here. Like now is the energy at the location 2 is equal to the energy at the location 3 plus the energy lost like in the process, in the moving process. So like energy is keep losing, so that is 23.44 minus 20. So up to this point, only 3.44 pound-feet energy left. So it's like when the block moves from the original location to the right, and then it's bring back to location A, only 3.44 pound-feet energy is left. So we're gonna do the same thing. It's gonna hit the spring A again and then be like, and then going back. And so first we need to calculate like how much deeper the spring gonna be compressed. So that is the energy at the third location gonna convert it to the energy stored in the spring K2S2 plus the energy losses due to the friction mg S2. So 3.44 is equal to 0.2, 0.5. Times 120 times S2 to the power of 2 plus 0.4 times 25 times S2. So 3.44 is equal to 60 S2 squared plus 10 S2. And then we can solve for S2.